Good morning and welcome to this looking back. This is the second in this series where we have the benefit of having people who have spent many years in the scientific career with the Raman Research Institute give their perspective of what they found fruitful, what they felt was something that they gained out of Raman Research Institute and what they gave back to the Raman Research Institute. And we have Dr. Raghu Nathan. Sorry, I'm sorry, I just came running from Raghunathan. And Raghu, who has been here for many, many years. So he joined RRI in 1991. Right, 1990 as a project assistant. So to all project assistants here, it means a lot. And he had a great career here. So let me just recount that he did a bachelor's degree in science from Mysore University, engineering degree in instrumentation technology from Bangalore University in '89. And then I believe he moved here and also did his PhD during his tenure on investigations of techniques to detect cosmological backgrounds. And I'm personally delighted that he built something here which looked for the cosmomicrowave background radiation at 1280 megahertz. But he has been involved in the development and design of several state-of-the-art radio receivers for telescopes like GMRT, and others which are at Gauri-Bidnur. And now, in the last decade or so, or maybe more, he has been involved in another frontier area which is emerging. This is the search for the cosmic dawn. Okay, and I'm proud to say Raman Research Institute has a great lead over the rest of the world. We have this very unique series of experiments deployed on the ground. We are ambitiously planning to send something to space. And Raghu has been a major player from the electrical engineering group in this whole effort. And I know that a lot, the team owes a lot to his dedicated work during this period. Also, have been very, piqued by the big radio antenna he keeps bringing to the ground early on the lawn. That's the first time I saw one of these major antennas, which Raghu tells me are designed to be better than the low frequency antennas that will be deployed for SK. So I'm really delighted that our, members of the scientific community here are challenging what's globally the frontier. And that's how we should be doing science. I won't take too much time. Again, let me welcome Raghu to give his talk on looking back as from his perspective. Thanks.
Thank you very much for your kind words and introducing me to the community of RRI, which is a mixture of newcomers and old people. All right, so basically let me introduce myself. I am purely an engineer. Instrumentation technology is my background. I joined RRI with that degree with a hope of using my engineering knowledge for conducting scientific experiments here. That was my hope before joining. I did not know what I will be doing after joining, but from an outside point of view, this was my wish. With that, I joined, and then never repented for having done it. Have been enjoying my life, continue to enjoy my life even after retirement, continuing to do what I have been doing. All right, thank you very much for the welcome. So I will begin my engineering journey by saying that my entire contribution is from an engineering perspective because of my background. The entire work revolves around the engineering activity. Basically, I should say that I should concentrate mainly on the analog domain. That has been my interest, and I worked only in that domain, major portion of it. So doing either building instrument or building new technology, adopting it to the new receiver system for the radio astronomical purpose, whatever you call. So mainly I would say that these are all engineering, and I also wanted to use whatever I built for doing some amount of science which I called, that's all, may not be a core science like what you all do, but little bit to my satisfaction, which involved measuring the cosmic microwave radiation temperature using the geometry receivers that I built. And of course, being part of a core group, doing a core science in cosmology itself was a benefit to me, itself was a nourishing to me, and I would say that I was fortunate to be in that group who did great amount of experimental cosmology. So, and then of course in the last part of my career, I involved greatly in the development of new techniques which have great implication, great application as in the low frequency domain. So these are all the four elements, four areas which I have mentioned. I'll go one by one to an extent of giving you what I did mainly. So GMRT, begin with the GMRT. GMRT, as you all know, is a national facility for conducting research in the field of radio astronomy. It has a wide frequency coverage, very, very versatile instrument for conducting or doing the science or say observing the sky starting from 50 megahertz to 1420 megahertz. And this is main goal, if you ask why was it built? It was built to detect redshift at 21 centimeter line as number one, number two, and do search for rapidly rotating pulsars in our galaxy. In addition to this, there were other astronomical phenomena which are of great interest to other groups. So our contribution to GMRT in the very beginning in 1990 was to build a 21 centimeter receiver system and give it to GMRT. Give it to NCRA, I should say. NCRA was the research institute which took up this challenge of building this national facility. So in the beginning, they never wanted a receiver system going beyond L-band, that means going beyond 1000 megahertz. But we took up the challenge of building that. Our contribution to nation, to the National Radio Astronomy Committee was to design and build 21 centimeter receiver system, which has been working even now consistently, giving equal performance from that day. So the person behind this is Professor Sharma ji, okay, and he took the entire responsibility of designing, developing the 21 centimeter receiver. So what I have shown on the left is a prototype which is there in the lab, and that is what we built. And each one of these is sitting at the prime focus of the GMRT of the GMRT dish, okay, and looking at the sky. So when I joined this group. I did my job. My first job is to work on 21 centimeter receiver system, design, be part of antenna design group, be part of various RF modules which form the part of front-end receiver system. So what I'm showing right now are the key ingredients, key points, key modules of 21 centimeter receiver. Basically, this is the feed horn. This is a very wide beamed antenna sitting at the top, looking at the sky, covering a large frequency range. Ours was the only largest bandwidth that the receiver system supported, and this is the corrugated feed horn which we developed the early days. Right now, even it is there without getting replaced by new one. And these are the frequency independent characteristics of the dish of the antenna, and which is absolutely required to determine the quality of the dish. And this is the low noise amplifier. What is most important, one should understand, is as you go higher and higher frequency, receiver temperature bothers quite a bit. What we all attempt to do at high frequency observation is to design the receiver system which has got very low inherent noise of itself. So it was really challenging for us to develop an antenna, to develop an amplifier which has got very low noise of its own. So the amplifier which is shown here is the one which we developed over past 5 to 6 years during 1990s, and it has got a noise temperature of about 25 K, remember, at ambient temperature. Even now we don't have a we don't have an amplifier which is having temperature lower than that unless you cool it. So this was an ambient temperature low noise amplifier working for giant millimeter wave radio telescope at 21 centimeter. And what you see here is the noise temperature which is almost constant for our frequency range. Okay, between 25 to 30 is the noise temperature of this amplifier. Of course, several groups worked on it, so students worked on it. I cannot name all of them, but people who are key persons are Sita, who is not here, and Sandhya, part of our group, and various other people. So these are again part of another module which is a band pass filter. I told you earlier that our receive system had a large bandwidth going from 1000 to 1400 megahertz compared to all other receiver systems which have got a bandwidth, very narrow bandwidth of about 38, 32 megahertz. So this is the amplifier, this is the band pass filter where you see all these four representing the filters at different frequencies, and these can be switched at will. Okay, either if you want to observe at 1170 megahertz, you can do it, or 1280 megahertz or 1380 megahertz. So you have a choice of filters which can be chosen at your will by giving some controllers. So we had this liberty of giving the user a very wide band so that he can place his observation anywhere in between 1000 to 1400 megahertz. Okay, so we had another feature which none of the other systems had, was observing the sky at a wide band simultaneously. So by passing all these filters, we had only one filter covering simultaneously 1000 to 1400 megahertz, which is this. Okay, so in principle you could have observed if you are capable of processing the entire band or as large as 400 megahertz is the choice that we gave to the user, and this is the filter which gave that option to the user. So this is the wide band pass filter, and this is the response of it. So with all these features, this dish was characterized, and what you see here is the table which tells you mainly two things. One is the system temperature, which determines the sensitivity of the receiver to detect weak signal, and of course efficiency. Efficiency basically boils down to how good you are utilizing the dish surface for collecting the radiation. Two things very important, and if you see here, dish efficiency is around 35%. Okay, if you see all these things, these are all 35%, and system temperature is between 60 to 70 K, which is large compared to other telescopes existing, which have got lower system temperature. So with these limitations, the observation went on. Even now it is going on. Not that it has improved quite a bit, even now it is going on, but this was known to us in the very beginning, and we wanted to know how to address this. So three proposals we had in our mind to improve this. One is to use a completely separate feed horn to illuminate more the dish surface so that you get more efficiency, number one. Number two, since the temperature, receiver temperature is more, can we cool the receiver is number two. That means if you cool the receiver, system temperature is expected to go down a little bit. Okay, that is second option. Third option is, have more or less porosity in the reflecting screen. If you have less porosity, the ground noise coming up will be reduced. These were three options we had in our mind, and when we proposed this, the third one simply got rejected because of wind load that the antenna was designed. When TCS designed it, it had some threshold value of wind load for that side. If you increase the mesh and becomes more and more opaque, wind load becomes larger. So dish was not designed for it. So this was not taken up. Then first one, that means replacing the existing feed horn by a new feed horn was also not considered because of other poor electrical performance. So given this, we had only choice, we had only second one, which is try if you can cool the receiver. That was the only option, and with that option, we just went ahead with the IAC, CCT department, Center for Cryogenic Department, and saw if we can come out with a compact cryo cooler which can be placed at the prime focus of the dish so that you can cool the electronics sitting there. So with that intention, we developed a compact cryo cooler. Everything went on in the lab, and then we showed in the laboratory that if you are able to cool it, then you have achieved what you wanted. So we did that exercise. This was this was purchased. A twin piston cryocooler was purchased, and we built a vacuum jacket, and we placed it on it, and LED was mounted on it, and this is a self it doesn't require any cooling, any tube from outside. Okay, it has the cooling, everything is integrated in this. Okay, the cooling, everything is a part of it. So when we cooled the LNA to low temperature, what we saw was the sudden drop in the temperature as expected. This figure shows the LNA temperature variation as a function of the ambient temperature at various frequencies. So as we expected, the noise temperature went down, and of course went down to about 10K, 15K. This was in the laboratory. So with this demonstration, we went to a dish, 4.6 meter dish, which was sitting on top of our dome building and mounted on this, and of course cooling. So why did this exercise was, we had to put, in case this option was selected to improve the performance of the geometry dish, we had to put this cryocooler at a height of 18 meters on geometry dish. So keeping it at that height and keeping the circulator or bringing down the signal was the challenge for us. So to just simulate what is existing in geometry, we did this of keeping our compact cryocooler at the prime focus of 4.6 meter dish, and then cooled it. So when we did this experiment, this is what we found. The LNA which was uncooled was around 180K, and when it is cooled, it went from 214K to 180K. That means this T system is a combination of inherent noise as well as ground noise coming from outside. Okay, it is not only the LNA noise, but it is combination of noise coming from outside in addition to what it has got. So we see clearly a reduction in the noise temperature from 214 to 180, but we should see this, that net reduction is not drastic. This is what we should observe. So since the net system temperature is dominated by ground noise, simply reduction of noise temperature of LNA alone will not bring down the net temperature. This we knew it, but We just wanted to at least prove it, that at least by cooling, you improve some percentage of efficiency. Okay, so this was our demonstration, and we proved that it is indeed possible to improve the system temperature if you cool it. Okay, this proposal we put forward to GMRT, and at that point this was postponed, or it was not taken up. At least from RRI side, this proposal we demonstrated it and then gave them the solution.
How much has been looked into the change of mesh in terms of wind loading? Because does the mesh necessarily have to be homogeneous? I mean, can't you pattern it such that the wind loading and response are kind of balanced? We find a trade-off between wind loading and so roughly, I mean, you may have.
See, given the mesh dimension of 10 by 10, 15 by 15, 20 by 20, as you go from vertex to outside, the maximum wind load which it could sustain was 70 kilometers per hour. If I had increased or decreased 10 by 10 to 5 by 5, or even the next periphery from 15 to 10, it would have gone beyond. So it was not designed for taking that much of wind load at that site. So TCS made it very clear that it won't sustain. It may collapse. So Swaroop never took a chance of replacing it. Even this was there in his mind, but he was helpless.
Okay.
All right. So this was the phase, my first phase, from 1990 to about 1998. All these things, happened. About 8 years consistently, even in the lab worked. We produced 30 numbers of receiver systems for 30 dishes. We all went to the, ton by ton to the field, put them all on the dish, characterized them, and made sure that everything was working as expected. So the next phase started when I wanted to use one of my receivers, one of the 21 centimeter receivers for for getting my higher degree, which is basically my MSc by research. So at that point, Ravi was here, and he proposed that we can slightly modify the existing 21 centimeter receiver to measure the CMBR temperature. And this was this is the experiment which I am referring to, which gave me, which formed my thesis for my master's degree. So what you're showing, what I'm seeing, what you're seeing here is the GMRT feed. If you see this, this is the flared section which I'm referring to, and if you go back here, and that portion has been removed. That flared portion has been removed. Okay, we removed the flared portion of the feed horn, replaced by a simple plate. Okay, the simple plate with corrugations, like you see here. This is basically a side view of the plate which you see here, and you have ridges all around. That's all. We never used the original feed of GMRT as our feed for CMBR experiment, mainly because the reason that we wanted to measure absolute losses of all the modules in the receiver chain, because remember, we were trying to measure the absolute value of the CMBR temperature. What you measure from the sky, unless you separate out the components involved in it, you cannot get back to the level of few Kelvin. So the temperature, the total sky signal that you measure will be a sum of several components, starting from foreground, they include and your atmospheric contribution. Then you have ground contribution. You have noise temperature. Because of the system. All these things you should know to a precision of half a Kelvin. If anything you miss out, then you are done. You cannot get a value closer to CMBR temperature. because it will be much larger. Therefore, it was our intention not to use anything in the receiver chain which cannot be calibrated, whose properties cannot be found out. Therefore, the flared function was completely removed. We simply had one waveguide. Waveguide can be easily characterized, because if you put this, basically a simple tube, you can put two tubes attached to each other, and you can characterize, you can get the loss of it. So with that, because of that requirement, we remove the horn and simply use the tube as a feed for our experiment. And that is how you see this feed replaced by simply a tube, and you have a plates all around. The intention of that is to minimize reflection coming from horizon. Okay, these corrugated rings act as a high impedance circuit which produces a very high impedance for the signal coming from ground. Okay, so it is our responsibility to make sure that anything away from the sky doesn't enter into the receiver system as an undesired signal. So with that intention, we put a plate with corrugated plate whose height determined the frequency at which you are measuring, and also it offered very high impedance. All right. So these are the modifications that we did for the feed horn. Number 2 is introduction of a circulator. Bit technical, I will have to say this out because of this is the crux of my work. We introduced a circulator. A circulator is a device which doesn't allow signal in the back and forth. That means it is not a unilateral. Okay, what goes in one direction will not be traced back. All right. So this is the circulator. Any signal coming from here will go here, but any signal coming from here will not reach here. This has very significant importance because any reflection in the signal path will have a tremendous effect on the passband response of the instrument. It will give rise to structures in the passband. It will give rise to undesired components in the passband, which goes as undesired temperature, which needs to be calibrated. If you are not able to calibrate, if you are not able to know the origin of some signal, you cannot get on to the measuring the ambient temperature. So we have to, every component in the signal path should be known to you. Anything goes, you cannot do it. So that was the intention of making sure that signal path is clean. So circulator helped us doing that. And in addition, it also acts. It is a 3-port network, and the third port is normally terminated in 50 ohm system, and the main drawback of any 50 ohm system is it produces 300K, which is disastrous. If you are measuring temperature in the order of few Kelvin, having 300K, where will you go? You cannot. So therefore, we had to replace this termination temperature from 300K to as low as possible. So the technique we used to have a load at very low temperature without cooling it is to point towards the sky. You connect it to the feed horn. Feed horn is looking up the sky. Sky is a cold load at this time, at this frequency. Look, it is as cold as 3 Kelvin, 4 Kelvin. That's how what best you can get cold load. So the circulator, whose third port had to be connected to a cold load because of minimizing the noise contribution from that load, it was connected to a sky through the feed horn, and of course, without even your knowledge, you had achieved cold load. So that was the intention of this, and another one is once you connect it to the sky, you don't have control what comes from the sky. So what comes from the sky to this will enter into the receiver. Okay, but once you enter into the receiver, you will not have any estimate of it. So you have to cancel it. If you want to cancel it, you cancel by introducing another signal with a 180-degree phase. So by doing this, we cancelled it, the signal coming from the sky in this path. So that is this extra cable. So all these techniques went into this, and finally we could get a temperature about 3.4 K with uncertainty of plus minus 0.4 K. Okay, so it may appear very trivial, but measuring absolute temperature is not easy, because every bit of it you should take into account. Okay, going down to 3 Kelvin is marvelous. Okay, the amount of K that you take is really very much large. So what I am showing here is the temperature measured by other groups across the globe at that time, and they're all, we know right now about 2.73 K, it's taken for granted, but at that time, we wanted to reconfirm from other measurement that it is indeed, that's all. Basically, it adds on to the statistics. Okay, we don't see anything new, that was the intention. Of course, the engineering went into it, is marvelous techniques. All right, so this got over, and our paper got published in JAA about these things. All right, so that was the second phase. So third phase came up when Govind Swarup proposed a technique. This is basically an era when SKA was coming up, flourishing it. Okay, so Swarup did propose a technique which could be used in the place of dishes for observing the sky at a few hundred megahertz to 10 gigahertz. So his technique was simple. His main intention was to design a parabolic dish which is lightweight, cost effective, most important, solidity ratio. If you have less solidity, that means a volume to mass ratio, if you have less, you can easily point very fast in the different direction. You can scan the sky very fast. It has all the advantages of making the dish low, making the dish very light. So with all these requirements, he came up with a design in which the backup structure which you see in the rest of the traditional radio telescopes replaced by a simple radially going ribs which are stressed, which are preloaded. Okay, what you see here are these radial tubes which are going from center to periphery. They're all stressed, they're all loaded and connected to the periphery. At the top, you have a ring connecting all these. So the main principle in this is when you stress a beam, it takes almost a parabolic shape. Once you have parabolic shape, you can keep facets on it, use it for surface. So this was the technique Govind Swarup came out with, and RRI came forward to build it and validate the concept. Okay, this was the next project I was involved in, and this was supposed to work from 150 to 10 gigahertz, and entire lab worked for 5 years continuously, and we developed several fields, which is L-band 0.6 to 1.7 gigahertz and C-band 4 to 8 gigahertz. We developed the receiver systems completely, and LONAS amplifiers, control system, everything required for the radio telescope operation we developed here. Okay, and then we tested it, and then did some scan across the source to know the efficiency of it. Okay, all right. So few words about how it ended. After doing all these things, I think electronics wise, we validated the functionality of the receivers, and digital systems was taken up by my colleagues, and it was the last thing required of course, I should say that Krishnan, along with Rishin, Gopal Krishna, Krishnamurti, they all worked very hard to design a control system. So finally we ended up with a limitation of dish not able to sustain its circularity as a function of elevation angle. Okay, normally we expect the dish to be rugged, independent of where you are looking at. Okay, it should not crumble as you go down in elevation, in zenith angle. Okay, but this dish had this limitation of becoming non-circular as you go away from the zenith angle, away from zenith. Okay, so the effect that this has got is in not having one pointing model for the dish. Okay, if it becomes non-circular, different elevation angle, what pointing model you will end up with doing it. Okay, what is required in any radio telescope is a model which will tell you the offsets involved if you want to position it in a particular direction. Modeling is very much required. Pointing model is what we call is the major activity people will do once dish is built. This had that limitation of losing circularity. It used to lose shape at different elevation angle. Okay, so with the help of ISRO, we could get some estimate of the non-circularity, but correcting it was a bit difficult. Okay, but the exercise said that at least L band, till L band you can use this, but it was meant for 10 gigahertz. Okay, we never anticipated this limitation, but ended up with this, and it was a major exercise. Even to correct it, big effort was required.
The same situation now. The dish does.
Absolutely, yeah.
It will.
See, the dish should have been in the continuous operating conditions.
No, so suppose you get it back to operating conditions.
Oh, yeah, absolutely.
Isn't it
Same thing.
Now with the computational capabilities, can't you
L band
live
you
with
can
a
use.
pointing model which changes
Yes,
with the angle?
yes.
and
Till
then-
L band you can do it.
Hmm?
L band you can do it. 1000 megahertz, 1400 megahertz you can do it.
No, but why not higher? I mean, it just requires a more careful modeling.
Absolutely, absolutely.
So
That's-
people are doing that. I mean, it's very doable.
And also, it's a major effort. Unless you come out with a rugged model taking into account, you can do that.
People have been scanning at sub-percent level things with, the modeling of the beam over the entire sky is done at very high level and then folded in. You have to do that.
Sure,
So
sure,
what I'm saying,
sure.
the computational capabilities exist now to do it.
Correct,
isn't it?
correct. But working group is not there. But you need a separate group right now. Because
Okay.
for,
No, I'm just curious. Yeah.
for 1 decade it has not been in use, and everything has to be re-looked into. It's a major exercise.
No, I just wanted to get your perspective.
True, absolutely. So after this, that was again, at the end of that, in fact, part of that should have been, my thesis work. And also what to say, after seeing this limitation, we didn't know what to do, because we were expecting something to come out, do something useful for my thesis work, but we didn't know what to do. So fortunately, Ravi came at that time. Then he brought cosmological experiment along with him, and experiment in which I was involved is basically to measure the EVOR temperature, EVOR signal. okay, which is everyone knows that the world is after that, even now, detecting the epoch of reionization signal, which is as low as a few tenths of millikelvin in the frequency range of 100 to 200 megahertz, and having specific spectral signature. Okay, that is the plus point of the signal. Okay, so this cannot be confused with any other signal because of its spectral signature. That is known. No other signal has got this spectral signature. Okay, so if you are able to, if your measuring instrument has sensitivity going down to few millikelvin, measuring this is not a problem at all. But problem is in going down, taking down the sensitivity of the measuring instrument to few millikelvin, which is the struggle we are all undergoing right now. Okay, so this was the problem I took up, and measuring instrument. So these are all the challenges. Measuring instrument should not have any spectral feature in its passband, which might confuse the detection process. Because if the passband has certain features which may look like the UR signal, you will get confused. Whether you are measuring UR signal or instrument bandpass, you will not know. Therefore, instrument bandpass must be flat without any structure. It's one of the main important points. And for that, the antenna that you design, the antenna that you use for detecting the sky signal should not have any signal, so it must be frequency independent antenna. Reflections, these are all the problems involved in the detection. Reflections will give rise to passband. Distortion should be minimum. And ground noise, again, we are talking about few millikelvin. Ground noise is few hundred Kelvin. We should minimize it. All these things are absolutely important. Loss of signal because between antenna and LNA should be minimized. Any noise, any absorption will give rise to noise. So with all these very stringent requirements, started building a receiver system. So we had two options. One, you go for a measuring instrument, single antenna based, which is this, and measuring instrument, two antenna based, which is this. Each one has got its own plus and minus. Single antenna is simple, okay, easy to build, but suffers from non-monotonic variation of the receiver noise. Main thing which bothers you in the single element receiver system is its own noise. If it has its own noise varying abruptly, how will you calibrate it? Difficult to calibrate. That's the main limitation of the single element. But in two element, when in two elements, two antenna outputs are correlated. When you are multiplying this, they are uncorrelated. This cancels out. You get rid of all the instrument noise. So that's the main advantage in this, but it has poor sensitivity. Each one has its own limitation. So of course we did both of them and did show to that extent, to their capacity, it worked. So first element, single element I took up and then built frequency independent antenna, which is shown here, having, you can see this, the radiation pattern of this antenna spanning over octave band has frequency independent characteristics, which you see all the frequencies are superposed on one another, they are frequency independent. That means antenna is not introducing any spectral features of its own for the passband of the instrument. Okay, that's what this is telling you. And this is the impedance characteristics of it is smooth. When it is smooth, you can expect not to have any reflections or not to have any spectral features because of the impedance mismatch. So we build this. These are all high impedance, very high dynamic range. See, what we require is a receiver system having a very high dynamic range in the sense that when you are looking at the sky, you will be measuring 3 millikelvin, you will be measuring 5000 Kelvin simultaneously because sky is bright at this frequency. So few thousands Kelvin come up, and in the plane, the presence of that few millikelvin has to come up. So there is a range of millikelvin to Kelvin. So 50 dB, 60 dB dynamic range is required for measuring it. So you need a receiver system as having dynamic range as large as this, still working in the linear mode, and that is what this one is. We built it accordingly. This was a custom built receiver system for that purpose, both digital as well as analog. And then we did some measurement. Finally, it ended up, it was very primitive to say that our first experiment in the process of detection, we ended up having we modeled. What we did was we collected the sky data, we modeled the passband response, we removed all known noises, and then fit the response using some lower order polynomial. What remained was this: we expected RMS if the signal was only CMB, we expected RMS to be around few tens of millikelvin. We ended up few Kelvin because of many things. It was still not matured in the sense of minimizing all the systematics, making all the elements frequency dependent. So like that, we had, instead of few tens of millikelvin, we had few Kelvin, and we stopped there, saying that it had to be improved if you want to take it forward. Thus, this was the output of the single element. Then we went to two element, as I told you earlier. In two element, we have two antennas placed together, and two antenna, definitely when you multiply both of them, will not have any passband response effect because of their uncorrelated noise, but I saw poor sensitivity. This
because you say in Kelvin, you are measuring voltages, right? Are you? No, not at all.
What do you mean? What
Like when you have this analog front end, it's an amplifier.
Yeah.
And you are also speaking about its dynamic range.
Yeah.
So my question is, this is measuring a voltage, right?
Basically measuring the power.
Power, yeah. So like, can you convert to voltages, for instance? See, there is a dish looking up there, and there is a signal coming in. The radio wave is coming in. And so this has to convert to a voltage, right?
Finally, what comes down? Yeah. What comes down is a voltage only.
Yeah.
Okay. We are interested in the power of the signal, which has got that spectral characteristic.
Yeah. So I just wanted to know, like, this could be even simplified to another simpler question. See, we have all these D2H, all those satellite dishes which look at, that's where we get TV programs at home.
Yeah.
So, of course, I guess those voltages are much higher than what you get here.
Yeah.
So, any idea? Like, just wanted to, it's a curiosity question, nothing. Maybe a few millivolts is that you get there. You have the LNB there and all that, right?
See, millikelvin divided by 50 ohms, square root of it is the voltage.
Yeah, that's what I was asking for. Okay, thank you.
So what I'm showing here is, this is important, okay? This is basically the response of the two element interferometer to a background whose temperature is constant. Because our signal, CMB signal, is homogeneous, constant across the sky, and what the interferometer responds to a constant input is simply this. What it shows is, as the distance between antennas keeps increasing, your sensitivity for constant input reduces. Therefore, in principle, the spacing should be 0 to produce a signal for a constant input, but in a two element, you cannot bring the antennas close to 0 because of its own limitation, mutual coupling. It has to be at certain distance, and that determines what signal it produces. So, low level with very low sensitivity, very poor signal it produces. Okay. So where do we go? It has got its own poor sensitivity limitation. What do we do next? All right. So Ravi Subramanian and of course Raman came out with another new idea of introducing a beam splitter in the sky. When you introduce a beam splitter in the sky just above antenna, not forward to antenna, just before the antenna in the sky, this acts as a component which gives zero component information to zero baseline information. What you require, you should understand, what you require, our entire CMB temperature information is lying here, is lying at the zero baseline. But we are unable to get it because of the separation limitation. So this screen is able to give the antenna information at this. It can be viewed this way. If you have a screen like this antenna, it may act as a partial mirror. This antenna will superpose on this antenna if they are equally distant, equally separated. When you have this antenna superposed on this, when you multiply this and this, you are multiplying two antenna outputs which are just superposed on each other. So it can be thought of like this, and what it produces is a zero component. So this was the understanding, and what you see here is the deflection or the receiver output with and without screen. So what you see blue line is the response of the receiver system when the screen is introduced, and red is the response without that. So it demonstrates very clearly that the screen has indeed enhanced the response of the interferometer for a constant input sky. So this demonstration we could do, and of course we ended up there because of the time limitation. So further on, I got involved in the same field of designing antennas for EVO signal detection, but for a wide bandwidth. We were all my work earlier was limited 1 octave, but we went ahead to more than 1 octave, 2 octaves, and this is a typical antenna working for 40 to 200 megahertz, and it has smooth response, but over 40 to 200. Remember, this is a wide bandwidth, and the residual that it leaves out after fitting it is not to the mark. It was slightly short of what really wanted. What we wanted was, after you fit it, the residual, the RMS value should have been much less than the EVO signal. So it was 1 order less than that, and it's some limit. But more important is, since this was kept on the ground introduced its own structures on which you don't have any control. So therefore, having antenna on the ground was a big problem for us. We could not model Earth properly, either through software or manually. This was major setback or limitation because of the antennas placed on real Earth. Okay? And we tried on putting on water, because water being a homogeneous medium, we thought it would help, because we could model antenna water more better than Earth. We tried designing antennas on water, and finally, and of course, we also see at that point there was a climb. This edges. It's another major team, working in this group. Detected. So they made a public, announcement that they detected a feature which is there in the original EVO signal, and which is this basically, which is this. And the dip, the magnitude of the dip that they detected was extremely large. Okay, so this came up as a big news, and our interest shifted, from our large bandwidth to narrow bandwidth to confirm whether what they are doing, what they are saying is right or wrong. So we went again to the design of antenna confined to a narrow band between 50 to 100. We tried few antennas on the ground. Finally, we ended up having an antenna water-based. That means knowing water as a good medium, as a homogeneous medium, we said water is a good medium which can be modeled easily, so that everything will be under our control. So we did this, and finally our result, it had all the features required, and the RMS was about 20 millikelvin. This was the paper from our experiment. It appeared a year back, and we had our argument on our question on their detection. Then, of course, this is my last 3 years. Finish in a couple of minutes. So, last 3-4 years, we were involved in developing new techniques relevant for low frequency application, and those techniques were in the field of designing antennas, in the field of designing high dielectric constant composite medium, and in the field of designing analog beamformer. These were the three main things which took up and successfully completed, which I tell you as we go on. And what is the purpose of this? It is to, it can be treated as an astronomical facility having instantaneous very large bandwidth with multiple beams. It can be treated as a platform for testing many modules being developed for SKA. And in addition, if you are able to come out with compact delay line for phasing the antenna, very big advantage. And Raman lens is the third one, which replaces the traditional beamformer while phasing the antenna. So these are the antennas which we developed, low frequency and high frequency, covering a decade bandwidth, 30 megahertz to 360 megahertz, all in one go with two antennas. And these are the fabricated modules, some characteristics showing they are all frequency independent antennas over the entire 30 to 90 is 1:3, 120, 360, 1:3. So basically, if you have both of them, you have 1 decade bandwidth. Then these are all the front ends, and this is the result of the single antenna what we designed, where we could get the background. What you see here is the blue line is a fit for the measurement in all these three bands. Then we went, this is the one which I was telling you, water-based high dielectric medium, which has direct impact on reducing the physical length of any delay line. Okay? Any delay line, it depends upon the dielectric medium used. The composite medium which we developed has about 25 as dielectric constant. It reduces the dimension, reduces the physical dimension by a factor of 5, which is a great improvement when you want to use a cable of very long length at low frequency, and we were able to do this. If you see here, a cable, such a long cable having dielectric of just 2, less than 2, is equivalent to this much line, which is about 200 mm long. 200 mm long compared to 700 mm long is what we showed. This is another major development which we developed in the lab. And what we did, we wanted to demonstrate it on the sky. We took 2 elements and used it as a delay element between in one of the antennas, and we expected beam shift in the sky. Because of that, and what we see here is a beam shift. So this is a demonstration of what we developed in the laboratory of a delay line on high dielectric constant medium, and this is just that. We were able to do it. The next is, last is the Raman lens, which is basically a one-time domain device capable of producing multiple delay lines required for having multiple beams in the sky. So this is a multiple input, multiple output, and this in principle can produce, if there are 3 elements here, it can produce 3 beams in the sky. So this was produced, this was fabricated, designed and produced in the lab. This was some character being tested in the lab, some characteristics, and finally what do you expect? If you are using this in between the antenna and the receiver system, we expect 3 beams in the sky. And these are the simulations, and what you see is this. That means we looked at the galactic plane transit, and we saw 3 beams, one here, one here, one here. This is beam at the zenith. This is shifted off the zenith by about 20 degree as expected, and this is the beam on the other side by same amount. So, the effect of by seeing this Rotman lens function has been validated. So, this is able to produce multiple beams having wide field coverage in the sky. Is independently we used earlier delay line to produce similar beams, independent delay lines, and what we expect was simply a central beam and 2 beams on the other side, and we got what we expected. So, we have built several prototypes, antennas, array of antennas, and water-based delay lines, and Rotman lens, from concept to implementation, and we have successfully demonstrated their functionalities applicable for radio astronomy in a radio telescope, and in principle it can be taken forward to a big array, which may finally lead to a facility adequate enough to produce a good science from the reasonable size. Okay? And I stop here by acknowledging our director, Tarun Swarudeep, ex-directors Sridhar, Ravi Subramanian for their encouragement in providing me complete support in my work. Remain grateful to all the people, it's endless, mainly Ravi, Uday, Desh, so CRS, Shiv Seti, to name few who nurture me during my academic growth. Heartful thanks to all my colleagues in the lab, workshop, Elba Ibrahim, Gauri Bidnor, of course, Gauri Bidnor I should not forget. They are the people, they are the backbone for our any experiment in the field. I should not forget them. Their help is greatly acknowledged by everyone who visits Gauri Bidnor. And they were all with me in my endeavor. By saying this, I thank you.
Thank you, Raghu sir, for walking us through your illustrious career and also telling us about SKA, GMRT, and all the facilities where you and your team have worked. The floor is open for questions. Anybody who has questions? Any questions?
What next?
You should ask him.
Oh, okay. Okay, there's a question here.
Yeah, some of these ideas of using this beam splitter and detecting simultaneously with 2 antennas placed at equal distance and then cancelling the common factor and so on, these are also things which are used in optics and other fields. So when it comes to radio astronomy, what are the special challenges which makes it like not
Wavelength.
so commonly?
Wavelength.
Is a wavelength?
Yeah.
Okay. So then it comes
Oh,
to
absolutely.
the size and the design of the
Oh,
antenna.
absolutely. The coupling is so large, it's not easy to handle.
Thank you.
Any more questions? If not, I have a small story for the benefit of the audience to share here. So the GMRT, which Raghu sir was mentioning, faced an unprecedented challenge in 2020 when there was a cyclone Nisarga which was heading towards GMRT, and the NCRE people had never expected to face a cyclone. And guess what happened? It is so sound, it is built so sound and well designed. The GMRT not just sustained but also survived wind speeds, very high wind speeds. The cyclone hit on June 3rd of 2020 when all of us were in the lockdown sitting inside at our homes. So GMRT the next day functioned very well. So I don't think there's a more fitting occasion to thank the scientists and engineers who built GMRT. It also survived a cyclone. So a round of applause to all those who built GMRT. Okay, any more questions? Okay, if not, let's thank Professor Raghu, and I call upon the director to felicitate Raghu sir.
Thank you for a wonderful tour of your wonderful career. Very enriching. And I'm sure it's very inspiring for a lot of people here.
Yeah.
And as the tradition goes here.
Oh, thank you
is
very much.
a print of your
Absolutely.
work.
Thank you very much. Thank you very much.
Thank you so much.